All right, let's get started. So, concrete design, let's go through some quick announcements. So I mentioned this last time, so for those of you that were in steel, and this is probably going to be a common theme, apologies for repeating myself on a lot of this, but such is the nature of the beast. So I mentioned this last time, I'll mention it again. So the technical conference, make sure that you've got your resume turned in to Noah Morgan at Morgan 268 at Marshall by next Tuesday. If you are interested in having your resume included in the resume booklet that's on all the tables for the conference, okay? Also, if you are free that morning and you want to volunteer, it's a great way to rub elbows with potential employers. Make sure that you contact Logan Stacks as soon as you can to get on that volunteer list. Okay, so today I'm assigning homework 1 in here on tributary area and gravity loads. Steel has a homework as well. It's due on Friday. The homework in here is due the following Monday. So that way I'm not having homeworks due on the same day. Sound good? All right. Okay. Let me get the sign-in sheet passed around. So I am passing around the sign-in sheet, so make sure everybody gets it. So here's this. Okay. And we're going to continue our discussion. Yeah, I think you missed the sign-in sheet. All right. Okay. So let's get into it. We're going to hopefully finish our discussion of gravity loads and get into load combos and whatnot today. We might even get past it some, so we'll see. Okay. So I want to really briefly go back into our discussion of example 1 and the concepts of tributary area. So if you recall, that was really a big theme last time, was to discuss tributary area, how much floor area a given element is responsible for. So how much floor area is that particular beam responsible for versus the beam next to it. Long and short of it is it's just halfway over. So it's pretty easy to determine. The other important aspect of tributary area is that whole hip bone connected to the leg bone thing. The idea that this beam, for instance, is going to see basically a uniformly distributed load, and then the support reactions from that floor beam are going to be distributed to the girders that it's coming into. So this transfer girder here would see point loads, whereas the floor beams would see a distributed load. So making sure you're understanding that is fairly important. Now we did a load takedown of some basic elements in the floor system on the following slide. So we looked at the tributary area, and then we looked at doing some pretty basic analysis of the elements. And we looked at a typical floor beam, we looked at a typical interior girder, and a typical column. Did anybody have any questions on that or any issues? Anything at all? Okay. All right. What I want to talk about today is I'll do my best to try and make sure this isn't movie time, but I do want to go through some fundamental provisions associated with basic gravity loads. So dead loads, live loads, and snow loads. I'm going to somewhat briefly talk about lateral loads, wind, and seismic, but I've reserved the heavy discussion for wind and seismic in steel design. So for those of you that were in there, you know, we were spending the last couple of days pretty heavily talking about that. So between the two classes, you get the, for the most part, you get the full picture. All right. So just you know, sort of brief note, we're getting a lot of these load provisions from ASCE 7, and it's one of the most consulted documents in a structural engineer's library. A lot of the provisions from ASCE 7 wind up in other load documents like IBC and things like that. So it's a very worthwhile guide. Now we're not going to I'm not going to make you all purchase ASCE 7 or use it directly. I mean, the document itself is pretty expensive, but we're going to use some of the basic fundamental components of it. So I think this is where we stopped last time. We talked a little bit about dead loads. So dead loads are the basically the forces that the element is going to be responsible for, that are comprised of essentially its own self-weight and anything that's permanent, anything that's not going anywhere. So self-weight, the floor slab, some of the main components of the building like the drop ceiling and things like that. Basically anything that's stationary. Okay. Now, arguably the most common materials we use in civil engineering structures are steel and concrete. So it's one of those sets of numbers that I want burned into your memory. The idea that steel weighs 490 pounds per cubic foot, and a reasonable upper bound estimate for reinforced concrete is 150 pounds per cubic foot. I can guarantee you that's going to be on your formula sheets and all that, so that might be a star-worthy slide. Other weights you can find, either from ASCE 7 or maybe from the manufacturer. You know, I'd argue, for instance, if we were looking at, let's say, this drop ceiling, the more accurate measure of this drop ceiling self-weight is to call the manufacturer and ask them directly. They're going to know because they're the ones who make it. But in the absence of that material or that information, you can obviously refer to a guide like ASCE 7. There's just pages and pages of every conceivable construction material that you would use in a building structure. And next to it is a reasonable PSF load. When in doubt, just always use the upper bound values. This is where we stopped, so I am going to go through this again just to make sure everybody's clear on this. One of the most fundamental, if not the most fundamental load that all beams are subjected to are their own self-weight. So if I look at, let's say, a rectangular, prismatic beam, so the total weight of that beam is going to be the unit weight of the material, the 150 pounds per cubic foot or what have you, times the volume of that beam. So the volume of that beam would be B times H times L. Sound good? Now that's the weight, but if I'm idealizing that as a uniformly distributed load, then I don't need the weight. I need the weight per foot, the weight per length. So if I take that computation and I divide the length out, I'm basically just taking gamma times BH. And BH is nothing more than the cross-sectional area of the beam. So in general, if I need to determine the weight per foot of a beam, I would take the unit weight, the 150 pounds per cubic foot or what have you, and just multiply it by the area. Okay? Does that make sense? We're going to do that quite a bit throughout the semester, so I really want to make sure that makes sense. The only thing that I would point out is the one thing I've seen happen more, time and time again is the issue of units. For instance, concrete is 150 pounds per cubic foot, but when we look at a beam that's 12 inches wide and 18 inches tall, the area comes out in square inches. So pounds per cubic foot times square inches, that doesn't work. So you have to convert one of the units. Typically, we would take the area and divide it by 144 to get square feet. Does that make sense? I've seen that happen more often than not, so just make sure that you're taking that into account. Sound good? Okay. Let's talk a little bit about live loads. So live loads are loads that aren't stationary. They're not permanent. Another word for them is, another way of saying it is that live loads are transient loads. They're loads that move around. And essentially, the easiest way to describe what a live load is a live load is related to its occupancy. In other words, what is it being used for? Is it a theater? Is it a classroom? Is it a hospital? Is it an office building? Is it an ice skating rink or what have you? Dependent upon the type of building that you're designing, you're going to have a different live load associated with it. So for instance, if I'm designing, let's say, an office building, okay, so I've got a few loads here on the slide. So office buildings. Lobbies and first floor corridors are taken to be 100 pounds per square foot, whereas the offices are only taken to be 50 pounds per square foot. Does that make sense? I mean, think about it. If you're looking at a typical office building, wouldn't it make sense that the lobbies are going to have a fair amount more people in it than the offices themselves? I mean, you go into the office building, there's all this waiting rooms, all these big areas, for people to collect. But the actual office might have 1 or 2 people in it, right? So here's another thing. Look at this. Look at the corridors above first floor. The corridors above the first floor are 80 pounds per square foot. In other words, the hallways. Make sense? So the hallways have a little bit of a heavier load. In fact, in commercial building design, it's actually pretty common. If you're the structural engineer, you might be designing a commercial office building for some developer, and that developer wants to be able to divvy up that square footage of floor space and sell it to tenants in any way that he or she wants. So it's actually somewhat reasonable in structural engineering, if you're designing a commercial office building, to just treat the entire floor system as if it was one big hallway. So take the conservative approach and just put 80 pounds per square foot everywhere. That way, if a dentist's office or a law firm or an accounting firm come in, they say, well, we want the offices arranged in this fashion. Okay, the floor can handle it, right? And then the dentist's office says, no, I want the hallways and the operating rooms and the patient rooms this way. That's fine, the floor can handle that as well. So it gives the owner a little bit more flexibility to rent that space out to prospective tenants. Does that make sense? Are you okay with that? So it just depends on the aspect, depends on depends on the application for the building. So a little bit more at home for us. So if we look at schools, classrooms are designed for 40 pounds per square foot. Corridors above the first floor would be 80 pounds per square foot, and then the hallways on the first floor would be 100 pounds per square foot. Now, here's the problem with that. That's great. I got a hard time thinking about what that means. You know, I don't know what 40 pounds per square foot means in terms of people. Well, that's where this comes into play. So this is an image that actually comes out of the LRFD Pedestrian Bridge Design Guide, but it gives you a mental image or a mental understanding of what 50 pounds per square foot really means. So what they did is they roped off this 6 foot by 6 foot square, and they started stacking people in the square to start giving you kind of a mental image of what 50 pounds per square foot really looks like. That's 50 pounds per square foot, okay? That is 100 pounds per square foot, and then this is 150 pounds per square foot. That's a lot of people, okay? Now, okay, let's do this, okay? This is 50 pounds per square foot. That's approximately 12 people in a 6 foot by 6 foot square. Now, if you take a typical classroom in this building, okay, and you apply 40 pounds per square foot and use that analogy, asking yourself how many people would have to be in this room to reach a load of 40 pounds per square foot. And if you do that math, you'll find that roughly you're going to need over 100 people in this room to reach 40 pounds per square foot. So let me ask you a question. What's the probability that a room in this building is going to have 100 people in it 24 hours a day, 7 days a week? Well, that's a good point. You're exactly right. But in general, I'm talking more about from a loading aspect. Let me ask this question in another fashion. I mean, you're making a good point about fire codes, but let me ask you this question. Let's ask this way. What do you think just the probability that the floors will really experience those loads 24 hours a day, 7 days a week? Not likely. Okay, now let me ask another question. What do you so the live load for a library is around 150 pounds per square foot. What do you think is the probability that a library is going to see 150 pounds per square foot 24 hours a day, 7 days a week? Pretty high, yeah, because the book stacks are not going anywhere. So what I'm introducing, what I'm discussing right now is the idea of live load reduction. When you open up the spec and you start looking up the live loads for an emergency room or an ice skating rink or a theater, those are maximum recorded live loads that we see in typical buildings across the United States. But dependent upon your structure, you ask yourself, what's the probability that these design loads are going to be applied all the time? And the answer is not likely. So what we can ultimately do is reduce that live load to a more usable value for the purposes of design. And that's where live load reduction comes into play. So ASCE 7's expression for live load reduction is as follows. So what you would do is you would take the live load that you look up from the spec. So for a classroom, what do we got, 40 pounds per square foot? We would take the 40 pounds per square foot and we would multiply it by the following expression. And we would ultimately generate a reduced live load that makes a little more sense that we can use for design. So L is our target. That's the reduced live load. L sub naught is the unreduced live load. Now, it's a function of two things. The tributary area, which by now we should know how to compute, right? So the length divided by that halfway between each adjacent element. That's pretty simple. And then the live load element factor. We'll talk about the live load element factor here in a second. But these are a few provisions to go along with that. So live load reduction does not apply for cases where you have really low tributary areas. So if you're going to apply live load reduction, basically the code is saying you've got to apply live load reduction where it matters. If you've got a member that doesn't really have much tributary area, then you're not really going to be allowed to apply it. You're also not allowed to apply live load reduction anytime you have an original load over 100 PSF. So for instance, the library, okay? The live load for a library is 150 pounds per square foot. You're not allowed to reduce that at all because that's such a substantial live load that the code is saying, okay, you have to consider all of it. Make sense? Yes, sir. No, that's a good question. Can you apply live load reduction to bridge design? The answer is no, because the actual load model that we use for bridge design is fundamentally different. We're not applying a blanket, 40 PSF or 60 PSF. That's really not the way it works. Do you remember in structural analysis when we looked at that vehicle in influence lines, that vehicular model? That's the load that we use during for bridge analysis. And bridges are, hopefully, if you're designing them for vehicular loading, they're always going to see vehicular loading in some fashion or another. So that load, that concept of live load reduction really wouldn't make sense for a bridge. It's a good question, though. Anybody else? This is good stuff. Are we good? Now, one of the things about this expression, this is a very empirical expression. This comes from going out and actually measuring the response of buildings, for a number of years and seeing if you can fit an equation that represents that amount of reduction. So depending upon the values that go into it, there are possibilities that because it's empirical, you can get some funky answers. So regardless, if you've got, let's say, a floor beam, so a floor beam is only supporting one floor's worth of load, whereas a column might be supporting multiple floors. Regardless of whatever you compute, in live load reduction, you can't reduce it below 50% for typical floor beams or 40% for typical columns. So if I'm designing a floor beam and the original load is let's say 100 PSF, I could only go down to 40. I couldn't go lower than that. Does that make sense? Everybody okay with that? All right. The only thing that's new is this live load element factor, and it's pretty straightforward when you think about it. I actually want to draw this out and show you a couple things. So I want to look at a typical floor beam. Would you agree that the tributary area for that floor beam looks something about like this? Make sense? Okay, this is the tributary area. All right? Now, tributary area is halfway over to the next adjacent element. This live load element factor, it's basically sort of putting the blinders on in regards to a concept called influence area. And I think this was something that a student was asking about last time. Tributary area is halfway over to the next adjacent element. Influence area is all the way over to the next adjacent element. So if I was looking at another floor beam up top, let's say this one right here, the influence area would be all the way over to the next adjacent element and all the way over. Okay? So that's the influence area. Now, both of these floor beams are identical. All these floor beams are identical. So I could have drawn this on top of one another, but I wanted to keep them separate. All right? Let me ask you this. If I took the influence area and divided it by the tributary area, what would the answer be? Somebody said? 2. It'd be 2, right? What's the live load element factor for an interior beam? 2. That's what this is. It's just trying to relate tributary area to influence area, and that's it, okay? So, for instance, if I'm looking at a column, okay, can I go ahead and erase this? Has everybody got this? Okay. So if I'm looking at a column, okay, the tributary area for, let's say, B2, this interior column, is going to be about like that. That's the tributary area. The influence area is all the way over. Now, if I took the outer rectangle and divided it by the area of the inner rectangle, what would I get? 4. Look right here. For interior columns, the live load element factor is 4. That's all that this is doing. Okay? Does that make sense? Yes, sir.
So for us to apply the live load reduction, the tributary area for the beam, for the tributary beam, has to be at least more than
400 square feet?
The area has to be more than 200.
Yeah, the tributary area has to be larger than 200. You're right. So the question was, going back to this, if KLLAT has to be greater than or equal to 400 square feet for floor beams, that means the tributary area has to be greater than or equal to 200 square feet, and that's exactly right.
Do you have an example of a building or structure that has a floor beam that has tributary area over 200?
Well, that was this one. That was this one, because if we look at, that's a good question. So if we look at this floor beam, what's that tributary area? It's 10 times 30, so 300 square feet, so KLL is 2, that's 600. This is valid. Yes, sir?
So like, you said it's 50 load reduction here on the detail on the parking garage where we stationary?
I'd have to go into the spec, but my initial thought is no, because it's very possible that a parking garage is full, you know. So I'm not 100% as to what the lookup value is, but I'd say no. So I can't remember it right offhand. Like I can remember the office building one, and I can remember the lane loading on highway bridges, but I can't remember that one right offhand. So sound good? Do you have a question? Oh, everybody good? Okay, all right. So let me get rid of that. So the nice thing about live load reduction is it's very plug and chug. Just plug in your area in square feet, and that's all there is to it. It's pretty basic. And there's really nothing else left to say. I mean, it's a pretty basic calculation. One thing we'll try and do throughout the semester is we're going to do live load reduction on our first homework assignment, but past that we probably won't. Like once you know how to do it, you don't need to do it, you know, from here on out throughout the rest of the semester. So I'll try and make sure that I tell you if you're designing a beam whether or not the load is already reduced or not. In other words, if live load reduction's already been applied, you don't need to go through and do it again. So sound reasonable? Okay. All right. Last thing to talk about is snow loads. And snow loads are pretty simple. If you've got the right lookup tools, they're pretty basic. They come from ground snow load data that's measured all across the country. So there's a number of weather stations across the country that are measuring ground snow loads in various regions. So depending upon where you're at, it's another one of those environmental loads like wind and seismic. You're going to have different ground snow loads. I mean, obviously, we're going to have a different ground snow load here than Miami does, or Anchorage, Alaska, right? So there's going to be different conditions dependent upon where you're at. This is a snow load map, and I'd argue of all the ones that we use, this is one of the ones that's the more confusing one. I still don't know if I can read that and figure out what our snow load is here in Huntington. The nice thing is, though, is I don't need to worry about that. I can go to the following website, and it helps me out with all those calculations directly. So I'm going to pull that website up real quick. Ooh, we're not using Internet Explorer. Nope. I'm not a fan. Yeah, I need to. Okay, So this is actually the same company that does the one for wind. It's actually like this one's Snow Load at atcouncil.org, and I think the other one is Wind Speed at atcouncil.org. It's the same company. And basically, all they did is just digitize those maps and zoom and match them up to like Google Maps, so that when you put in a latitude and longitude, it can match your location up with a particular region and report the ground snow load. It's pretty basic. So going back, I'm going to go to Huntington, West Virginia. I'm going to plug in that latitude and longitude. Now, there's something special I had to do. What did I have to do? See if y'all remember. Negative on this one, right? That's a good question. Why is Alaska separate? Because Alaska has its own map. There are two snow load maps reported in ASC 7, one for the United States minus Alaska, then the second one's just for Alaska. Because think about it, Alaska, the snow loads are going to be much more extreme. So, it's going to have its own set of data. Alaska's a really nifty region to design structures in, because obviously the snow loads are exceptional. Most people in Alaska live on the coastal region, so the wind loads go up. And then Alaska is on the Ring of Fire, so there's earthquake regions there too. So they're just, yeah.
Why do they do that?
Let's move on. Okay, so here's what pops up when you put in Huntington. Now, if you look, see how there's this like red region that's being highlighted? That red region essentially corresponds to this. So if you look, you can almost even kind of see it. Like, see this little shape right there? Like, here, let me see if I can kind of draw it out. Like you can see that. Can y'all see that? Like that. Something like that. So Huntington is about like right there. So what's that? I guess I kind of see where you like, this is Florida, kind of. Yeah. Somebody said, okay, so we got whale. So when we come back to class, should we just find a spot on the lawn and just look at the clouds and see? Let it warm up a little bit. Okay. So in this particular region, based on this ground elevation, our ground snow load here in Huntington would be 20 pounds per square foot. So it stands to reason if we went far more northern in the country, the snow loads would go up. Maybe we hit 25, maybe we hit 30, maybe by the time we get to Boston or something, we're in the 40s and 50s or something like that. All right. So, can we look at Alaska? Well, actually, it's been a while. Let me see what it does. Okay, so Alaska. So here's Alaska. So it basically just lists a series of locations. I remember this now. So if you're in Anchorage, Alaska, you would be using 50 pounds per square foot. If you're in Fairbanks, you'd be using 60. Or what? Valdez. 160 pounds per square foot. That's you. Whittier, Alaska. That's some snow. Let me tell you. That is some serious snow load. I'm sure there's an ASC 7 guide spec on the design of igloos for snow loads. Okay, all right. So let me go through how you would actually determine the snow load that goes on the roof. Because keep in mind, everything that we're looking up is the snow load that's reported on the ground. Okay, that's not the snow load that goes on the roof. So to determine the snow load that goes on the roof, and for this we're assuming that we're dealing with a flat roof, and most commercial structures have flat roofs. If you have an angled roof, then you have to do your projection angle and split your load up a little bit. But in the end, it's pretty plug and chug. What I'm more interested in is that you understand how to do the flat snow load roof. So you would take the ground snow load and adjust it by a few constants. So first off, the exposure coefficient. We're going to talk about that here in a sec, but the steel design folks, I think you've actually kind of already seen this before. The thermal characteristics of the building obviously matter. I mean, if you're dealing with something like a greenhouse that had a heated roof, stands to reason you're going to have different snow loads, right? Make sense? And then last one is the importance factor, the risk category of the structure. So the exposure coefficient, in most cases that equals 1, but it's dependent upon where your building's at. Now, we talked about steel, it related to wind. It also matters for snow as well, because what do you think wind does to snow? Blows it off the roof, right? So dependent upon your exposure characteristics, are you in the middle of Manhattan or are you out in the middle of Iowa, you're going to have different wind characteristics on your structure, and therefore you're going to have a different means of accumulation of snow, or a different level of accumulation of snow on that roof. Now, in most cases, the exposure coefficient equals 1. You can go through if you want and read that. I mean, it's just going through various different positions. In most cases, your exposure coefficient equals 1. Your thermal coefficient usually equals 1 as well, but this is going into, like, for instance, if you were designing something like a greenhouse and you had a heated roof, obviously that's going to cause the snow characteristics on the roof to change. But in most cases, your thermal coefficient is going to equal 1 as well. The last thing, though, that really can impact your snow loads on your roof is your importance factor. So dependent upon your risk category of your structure, you're going to have different levels of design snow loads that go onto a roof. So for risk category 4, you're actually taking the snow loads and increasing them by 20% to account for the risk category of the structure. For you folks who are not in steel, I'll briefly go through this. So the risk category of a structure, it is used fairly regularly to increase certain environmental loads based on how that structure is going to affect the community. So worst case scenario would be risk category 4. So a risk category 4 structure is something like a police station, a fire station, a 911 call center, a hospital, things like that. Because if a structure like that fails, not only is that going to impact the people that are in that building, but that's going to impact the entire community. I mean, if the fire station fails, that's going to hurt everybody in Huntington. You know what I mean? Because next thing you know, there's a fire and there's no fire station, right? So that affects everybody. A risk category 3 is a structure where you have a large number of people in the building that might have an issue getting out. So theaters and maybe places with large lecture halls and stadiums and places like that are risk category 3. Also elementary schools or nursing facilities and things like that, where the people inside the building are going to have a hard time, maybe have a hard time getting out. That's risk category 3. Now, by and large, just about everything else is risk category 2. Risk category 1, that's the one with the least amount of danger. Those are things like grain silos and places like that, that if they fail, yeah, it sucks, but that's not really going to have a high degree of risk of to the entire community. So, make sense? All right. The only other issues that are worth addressing are things like snow drifts. So snow drifts is when wind starts to accumulate snow along a given geometrical barrier on the roof, things like the parapet or the screen walls around the mechanical equipment on the roof. So what can end up happening is you can have bunched up snow, so you can kind of see that right there, and you can have a triangular load. I told you all that we have triangular loads in real life in structural engineering, and you all are like, why are we doing these crazy beams with triangular loads and stuff? Well, here you go. You can kind of see it right here. I'll try and color it in a little bit. You can kind of see, there's this triangular component to the load right there. Now, obviously, they didn't design their roof accordingly, because this roof has experienced a failure. So this stuff matters. Well, it does. All right. Any questions? Ultimately, it's pretty plug and chug to compute this stuff, so it's pretty straightforward. All right. Sound good? All right. I'm going to really briefly go through some of the lateral load stuff. Just for you folks that aren't in steel design, I want you to at least have a general idea behind this. There are two main lateral loads that structures can experience, wind and seismic. Now, wind can have some serious impacts on a building, but what makes wind complicated is the fact that wind pressures increase as a function of the building's height. The taller the building is, the larger the wind pressures. So being able to account for that is something you really got to make sure you're taking care of. Now, the equation for wind is actually pretty straightforward to derive. Those KZ, K constants and whatnot are actually just adjustments. 0.00256 V squared, that's actually just Bernoulli's equation. All you do is you treat air as if it's a fluid, so your unit weight is the unit weight of air. You have 0.1, which is the building, and you're trying to determine what is the pressure on that building due to a wind at 0.2 that's under a certain velocity. So you all remember Bernoulli's equation, you have 0.1 and 0.2. You set your elevation heads equal so they cancel, and solve for the pressure under a given velocity, and then throw a unit conversion in there to convert velocity in miles per hour to a pressure in pounds per square foot, and that's what you get. So pretty straightforward stuff. And that's really what I'm going to leave it at for us in here. I just want you to have a general idea behind where the wind speed equation is coming from. It's really not that incredibly difficult to compute. The last thing I do want to talk about is seismic loads. So when an earthquake hits a building, what ends up happening is you take the building and you force it to undergo a given acceleration. It's much like when you are in a car and you hit the brakes, you fling forward because you have undergone a certain change in acceleration, so you're forced forward. You then hopefully smack into what? Seatbelt. When I was first at Marshall, I asked that question to steel design, and they said the dashboard. And they said the windshield. Then they said the pavement. I'm thinking, you college-educated students, wear your seatbelt. Goodness. Hopefully you're wearing your seatbelt. Let's just leave it at that. Moving on. It built something, all right. Yes, sir. Generally, yeah. I mean, let me put it like this. In concrete design, you're going to be using different seismic systems than you would in steel design because obviously it's a different material and it's going to behave differently under failure. But the principle is still the same. It's just a different design philosophy because it's a different material. I mean, steel tends to want to buckle and fracture. Concrete beams want to and things like that. So it's a different set of mechanics. So does that make sense? We'll get into all that stuff, like how do we compute capacity of elements. I mean, that's the whole point of the class. So we'll spend a fair amount of time looking at that stuff. Something sound good? Okay. Now the only thing I guess I'll point out is a seismic problem is really basically distributing seismic forces based on Newton's second law. A building has a certain mass, an earthquake puts it under a given acceleration, force equals mass acceleration, and that's basically all there is to it. We distribute those seismic forces to the floors and then open up RESA and do our analysis. The only thing that you have to be careful of is where are you getting your accelerations? Well, it depends on where you're at. Obviously, we're going to have a different hazard level for earthquakes in West Virginia than we are in Nevada or California or somewhere like that. So luckily, there's some really nifty online tools that you can use to assess your ground accelerations and go from there. Sound good? Okay. Last thing we need to do is put all of that together. And that's where load combinations come into play. So load combinations are prescribed means to combine loads in order to address uncertainty. We don't just take, well, here's all the dead loads, here's all the live loads, here's all the snow loads, let's just add them up and call it a day. That's not how we assess design considerations in both steel and concrete. What we do is we take each of those load components and we combine them into the following load combinations. These load combinations are derived from all that probability and statistics stuff that we looked at earlier in order to try and address uncertainty and maintain a uniform level of safety. And that kind of makes sense when you think about it, when you start to look at some of the equations. For instance, these two ones that are in bold are by and large the ones we're going to use the most throughout this semester. I want to pay attention to the second one. Any floor beam in a building, you know, floor beams supporting loads up here, et cetera, are primarily going to be subjected to two types of loads, dead loads and live loads. Dead loads being their own self-weight, and live loads being for occupancy, what they're being used for. So let's look at that load combo as if all I had was dead loads and live loads. So 1.2 times the dead plus 1.6 times the live. So why is it that the live load factor is larger? I mean, why are we taking the live loads and multiplying them by 1.6, but taking the dead loads and only multiplying them by 1.2? I mean, why is that? Exactly. You know, if I look at this, let's say going back to my table analogy. If I take this table and I start to look at it from a dead load and a live load consideration, I mean, I could compute the dead loads for this table pretty easily. I mean, I could just go take it and put it on a scale, and weigh it, I can have reasonable certainty that those live loads are correct. Even if I didn't have the scale, this is wood, it has this dimensions, I could compute it, right? And I'm an engineer, I should get pretty close, right? I should be able to get pretty close. I may not be, super exact accurate, but I'm going to be pretty close. But if I then take this table and sell it to some end user, I don't know what they're going to use it for. They can put whatever they want on it, right? So I have more certainty associated with the dead loads, so I don't need to bump those up as much. The live loads, I bump them up a lot more. Okay? Make sense? Anybody have any questions about that? That's important stuff. Okay? That load combo, 1.2 times the dead plus 1.6 times the live, that is something we will use throughout the semester. Okay, guaranteed. Yes, sir?
Yeah, what does W and LR stand for?
Okay, W is the wind. Okay. LR stands for live roof load. And live roof load is basically just like workers and people like that on the roof. Because it has a different set of variability associated with regular old live loads, it's actually treated as a separate effect, but by and large, it's the same thing. I'm curious, does anybody have a guess what R stands for? Just guess. Anything. Think environmental. Rain loads. There's a really weird effect that can happen in structural engineering called ponding. Did I mention ponding at all last semester? Okay, so ponding is a really strange effect that I thought I'd mention. So if you have an instance where you have rain collected on a roof, that is a load on the roof. It has a certain weight to it and it's applying a load to the roof. What can happen is, so let's say you get to a point where you permanently fail a component of the roof because of that excess of water. So you've got a dip in the roof where there's an excess of water, right? What does that dip in the roof do? It allows for more water. More water means it's going to deform more, which allows for more water, which means it's going to deform more, which allows for more water. See how it kind of builds on itself? That's called ponding. So usually, though, if you detail your roof appropriately, you never have to worry about it. So that's usually why in most cases I don't want to say it's ignored, but folks like me really don't need to cover it because as long as you're detailing your roof appropriately, it shouldn't happen. So, but it's just something I wanted you to be made aware of. Yes, sir?
Case 6 and 7, why would you want to decrease 0.9 times the dead, that decreases the dead?
Because sometimes under those large winds and those large earthquakes, the dead load A, it might actually kind of help you during an earthquake, and B, depending upon your load, you can have uplift effects. So the dead load could sort of be acting in the opposite direction. I know that's sort of a strange way of looking at it. Let me also say this. These load combos, they are correct in their statistical, representation. But if we actually started really digging into the spec and actually digging into the wind provisions and the seismic provisions, it's a little more involved than what you're just seeing right here. I don't want to get too far into it, because we start doing that, then we start getting to the point where it's like, okay, now it's time to go to grad school, or now it's time to have a... No, I'm not kidding. This is stuff that we talk about in grad school, the deep provisions associated with how to do all the different wind load cases, how to do all the different seismic load cases, talking about ground accelerations and all this stuff. It's a can of worms at that point, but it also is really cool stuff. Yes, sir?
Would we have to take this into consideration? Like if we still have some parameters?
RISA does do that for us. In fact, do you remember in RISA when we did basic load cases? And remember at the end when there was load combos, I said just put a 1 in? You remember that? Well, what you would do in a program like RISA is you would build like a bunch of loads and say these are the dead loads. Then build a bunch of loads and say these are the live loads. It actually has all these already built into it, and you just hit a button and it factors everything for you. So you're right. A lot of software packages do this. But for a regular old floor beam, you need to be able to use the basic ones, so things like 1 and 2. Right? But if you've got a structure that has 5 or 6 different load effects on it, you've got all these different load combos to do, I mean, yeah, that's where software comes into play. You're exactly right. Yeah. What's that? Well, I mean, if we're talking about the lateral system and like the moment frame or the brace frame or the shear walls or something like that, I mean, any moment frame is going to have to resist lateral loads, but it's still going to also have to resist its own self-weight and all the gravity loads that are being framed into it. So, like moment frame elements, like the beams and columns that go into moment frames, are going to have to withstand wind and seismic, but they're also going to have to see dead loads, live loads, and snow loads as well. Does that make sense? I mean, let me go back a little bit and answer it like this. Okay, so this element right here, like this element and this column right here, okay, it is obviously having to withstand the forces that are framing into it, so the dead load and the live load coming from this beam, etc. But if this column and this beam were part of the moment frame, then they would also be subjected to the wind and seismic forces that are going on as well. So they'd be seeing a whole host of stuff. Does that make sense? Did you have a question?
Yeah. On the load combinations, the lesson is of these the maximum governance. So for this building, do we apply most in some cases and see which one is the maximum that we use?
Yes. So if you only have dead load and live load, you would have to do the top two, 1.4 times the dead or 1.2 dead and 1.6 live. And then whichever one of those two yields the largest answer, that's the one that you would use for design. It's a good question. Everybody else? Okay, all right, real quick. So what that is giving you is the factored loads. If you understand that, then what we'll do from then on, and what we're going to do throughout the rest of the semester, is learn how to determine factored resistances. And as long as your factored resistances are larger than your factored loads, that's the whole basis of our design, and that ensures everything is safe. After that, what we would then do is say, okay, what if we don't know what our factored resistance is? What if we're in design stage? The question is, how deep does that beam need to be? How much rebar do we need to place in that element to ensure that phi RN is greater than our factored loads? Sound good? All right, now, 2 quick questions before you leave, because I know everybody's leaving. Did everybody sign in? Okay, all right, because that turned into a little bit of an issue last time. Last one, homework. So, what's that?
Is that a question or?
No, I'm not. I'm giving it to you regardless. Besides, it's on MU Online, so I already have given it to you. your beeper? Yeah. Is it 1997?
You can still get them.
Okay, real quick. I know you all are trying to leave, so let me go through this real quick. So problem 1 and problem 2 are two different frame takedowns. Problem 1 has live load reduction components associated with it. Problem 2 does not, but the geometry is a little funkier, so you've got to go through and make sure you're understanding your assessments appropriately. Now, there is also a problem 3. I don't want you to miss that, but it's a really short one. It's just determining ground snow loads at the University of Maine. So, what's that? Not Alaska, not Alaska. So, all right, that's all I've got. I'm not going to see you all on Monday, so because that hurts. Right here, man. Right here, that hurts. We'll see you.